Hey everyone, my name is Joseph and welcome back to the section on decision trees. In today's video, we are going to be covering splitting algorithms. First, let's answer the simple question, what is splitting? Splitting involves decisions that are made through splitting nodes into subnodes. It's done until homogeneous nodes are left, which is when the classes are perfectly split. It's also the process of dividing a node into subnodes until the highest purity is achieved. Now, methods or techniques for splitting are classified based on whether the target variable is continuous or categorical. For example, if you are dealing with a regression problem, the target variable is continuous. In that case, when the target variable is continuous, one of the main methods you can use is reduction invariance. In contrast, when the target variable is categorical, there are many more options such as Gini impurity, information gain, and chi-squared. The first method for splitting that we are going to be discussing is reduction invariance. Now, for reduction invariance, the target variable is going to be continuous. As the name implies, it uses variance to decide which features to split on. A set of values with completely different numbers will have high variance, while a set of values with the same numbers will have a variance of 0. Now here are the steps to use reduction invariance. First, calculate the variance of each child node. Then take the weighted average variance of child nodes to find the overall variance. Then simply repeat the steps to find the best split with the lowest variance. For reference, the picture here shows bias, which refers to the assumptions made by the model to make the target function easier to estimate. Now here is the formula for variance, where x represents a sample, mu represents the mean, and the capital N represents the number of samples. Here's a basic example of using the reduction invariance method. The picture here is taken from Analytics Vita and considers data points of students who are indicating whether they want to play or whether they play cricket or not, which is based upon their performance in class. Now, in this example, we are first going to start with calculating the variance of the above average node. The mean of the data points in this child node can simply be calculated by doing 8 times 1 plus 6 times 0, as there are 8 ones and 6 zeros, and that all is divided by 14, which yields 0.57. Next, the variance can be calculated using the formula shown on the previous slide, which comes out to be 0.245. Then we do the exact same steps for the below average node, calculating the mean and the variance. Finally, we calculate the overall variance by factoring the fact that you can use 14 out of 20 and 6 out of 20 based on the two child nodes, as the total number of data points in this particular example is. For reduction in variance, multiple features can be tested until one with the least variance is identified. The next method for splitting is information gain. In contrast with reduction in variance, the target variable for information gain is categorical. Information gain also works with entropy. Information gain is simply entropy subtracted from 1. Entropy is also used to find the purity of a node. The lower the entropy, the higher the purity. Entropy is 0 for a homogeneous node. As impurity increases, the more information is required to describe a node. Now, what this means is that information gain is ultimately going to be inversely proportional to entropy. The steps for information gain are first, calculating the entropy of child nodes for each split. The next part is finding the entropy of split, which is the weighted average of entropy of child nodes. Afterward, simply repeat the steps like in a reduction invariance to find the best split with the lowest entropy and highest information gain. Here's the formula for information gain, which as we mentioned is 1 minus entropy. Now here's also the formula for entropy, where P sub I is the percentage of each class. Here's a basic example for information gain, where the example is once again taken from Analytics Vita, where the feature is performance in class, which can suggest whether students play cricket or not. Now the first step here is going to be finding the entropy for the parent node. By using the formula for entropy, we can simply do negative 0.5 times log base 2 of 0.5 minus 0.5 times log base 2 of 0.5, which comes out to being 1. Then we follow the exact same steps except for the entropy for the above average node. Once again, we do the exact same for the below average node. Now we can simply use the proportions of each node, that being 14 out of 20 in the first node and 6 out of 20 in the second node, as the weights for finding the weighted entropy. From there we find that the weighted entropy is going to be 0.959. Now, as we mentioned, information gain is going to be 1 minus the entropy. Doing 1 minus 0.959 gets you 0.041, which is the information gain. Like with reduction and variance, we can simply do the same process for other features to see which one has the highest information. The final splitting method that we are going to be discussing is Gini impurity. As with information gain, the target variable is categorical. Gini impurity is a very popular and simple method, partly because it does not have logarithms like information gain, which could be computationally intensive. Gini impurity is 1 minus the Gini value, where Gini is the probability that a randomly selected sample would be correctly labeled if it was randomly labeled based on the distribution of classes. Gini impurity is inversely proportional to homogeneity. The lower the Gini impurity, the higher the purity and homogeneity of a node. The Gini impurity of a pure node is 0. Now here are the steps to calculate Gini impurity. First, calculate the Gini impurity of each child node. Next, find the Gini impurity of the split by taking the weighted average of Gini impurities of the child nodes. Finally, as with the previous methods, simply just repeat the steps to find the best split with the lowest Gini impurity. Here are the formulas for Gini impurity and Gini. Gini impurity is 1 minus the Gini, while the Gini is the squared probabilities for each class or category. It is going to be the sum of each of those categories with respect to its squared probabilities for each of those classes or categories. Here's an example of calculating the Gini impurity with the same picture from Analytics Vita that was used for the previous method. First, we'll calculate the Gini impurity for the above average node. This can be done by taking 0.5 squared plus 0.3 squared, which yields 0.51. Then we can solve for the Gini impurity by just doing 1 minus 0.51, which is of course 0.49. We follow the exact same steps for the below average node. That comes out to 0.44 for the Gini impurity. Now we have to solve for the weighted Gini impurity. We once again do this by using 14 over 20 and 6 over 20 as the weights to solve for the weighted Gini impurity. This ends up coming out to 0.475.